We're swimming in this absolute ocean of data, right? Numbers are everywhere. But how do you turn all that noise into a clear story? Well, that's exactly what we're going to figure out.
I mean, it's a huge challenge. We've got endless information at our fingertips, but finding the actual story hidden inside, that's the tricky part. It turns out there's a specific art form designed for exactly that.
And that art is statistics. Think of it like a special magnifying glass we use to find patterns, a toolkit for making sense of it all. It's the bridge that takes us from raw, messy data to real, actual insights.
So where do we even begin this journey? Well, we start small. We start with the smallest possible piece of information we can get. We're going to look at just one variable and see what story it can tell all on its own. Let's use a super simple, universal example: human height. Okay, so if we measure just one person, we have a single data point. And on its own, that tells us, well, almost nothing. But what happens when that single point becomes thousands of points? This is where it starts to get really interesting. As we gather more and more data, all those individual points start to come together. They start to take on a personality, a distinct shape.
And just like that, what was just a long list of numbers transforms. When we plot thousands of different heights, a clear pattern emerges from the chaos. This shape is what we call the data's distribution, and it's our very first clue to understanding the bigger story.
Now, the technical term for this shape is a probability distribution, but really, it's just a map of likelihood. With this map, we can start asking powerful questions like, what's the chance the next person we meet is a certain height? This shape holds the answer.
And I bet you've seen this specific bell shape before. It's called a normal distribution, and it shows up everywhere from human height to test scores to tiny errors in manufacturing. It's one of the most fundamental patterns in our world.
Okay, so now that we found this shape, how do we describe it? We need a simple way to summarize its key features. Let's start right in the middle, with its center.
The most common way to find the center is by calculating the mean, which is just what most of us know as the average. You can think of it like a balance point, or the center of gravity for all our data points put together.
The whole goal here is to find that one number that can summarize the typical value in the entire data set. For our example, we're looking for the single most representative height.
But knowing the average just isn't enough. I mean, you can have two very different sets of data that have the exact same mean. The crucial next step is to understand how spread out or dispersed the data is around that center point.
And that measure is called standard deviation. The best way to think about it is as the typical distance a data point is from the average. So a small standard deviation means everything's clustered tightly together. A large one means the data is much more spread out.
This is where it all comes together. See, in a normal distribution, the mean and the standard deviation aren't just two separate numbers. They work together to create a complete, predictive map of our data.
And this leads to an incredibly powerful rule of thumb. In a normal distribution, about 68% of your data will always fall within one standard deviation of the mean and about 95% within two. This is so useful because it instantly tells us what's common and what's a rare outlier.
Okay, so now we have a powerful way to describe a single variable using its shape, its center, and its spread. But what happens when we introduce a second variable into the mix?
Right. What happens if we look at two things at once? For instance, what if we don't just look at height, but we look at height and weight together? Do they have a relationship? Well, we can investigate this by plotting height and weight on what's called a scatter plot. And look at that, a clear pattern immediately emerges. As height increases, weight also tends to increase. This relationship, where two variables move together, is called correlation.
But not all variables are connected. On the left, we see a strong positive relationship, just like our height and weight example. But on the right, the points just form a random cloud. Knowing one variable tells you nothing about the other. That's a classic case of zero correlation.
To actually put a number on this relationship, we use a score called the Pearson's correlation coefficient. It's just a simple value from -1 to +1. That height-weights plot would score close to +1, a strong positive link. The random cloud, that would score near 0, meaning no relationship at all.
So let's zoom out for a second and put all this together. We've just walked through the absolute foundational building blocks of data analysis. Now let's talk about why they're so powerful.
Think about the journey we just took. We went from a single measurement
to understanding the shape of thousands of them, to summarizing that entire shape with just 2 numbers, the mean and standard deviation, and finally, to uncovering the relationships between completely different sets of data.
So, why does all this matter? Because these fundamental concepts are the engine of modern data science. They power the predictive models that forecast sales, the recommendation engines that suggest your next movie, and ultimately, they are the key to unlocking the stories hidden in the data all around us.
From the price of your coffee to your daily commute, your life is generating data. And now that you have the basic tools to see its shape, understand its center, and find connections, the only question left is, what patterns are waiting for you to discover?